Let us go ahead and get ourselves started today. So welcome back for session 7 of 120B, 220B. I want to thank Afalabi and Gustavo for filling in last time and kind of showing you some of the tools that we were hoping to introduce to you. And we'll continue to play with them today. So if you happen to miss it last time and we don't have a recording of their session, we'll hopefully get you caught back up. We'll also go ahead and post links to the prior year's or prior quarter's session. So you sort of get a sense of what went on. But I think just most of that stuff we'll learn just kind of by doing as you try to practice on your projects. Today we're going to keep on talking about building envelope and kind of in Revit look at how you can use the modeling tools there to just illustrate some of the different things you may be thinking about for your envelope. So in particular we'll look at different sort of window conditions, skylighting conditions, curtain wall and mullion conditions, just how you can start using that tool to kind of model a lot of different things that you might want to consider as part of your building envelope. We'll also do a little bit of thinking about, or we're headed to, the notion of really what is the relationship between your structure and the envelope. And we'll start thinking about that. There are some choices to make about really, is your structure going to be completely buried in the walls and not going to be visible at all? Is it going to be on the interior of the walls where the envelope is really acting as a skin, kind of on top of the structure? Or is the structure going to be visible from the outside? And there's a little bit of thinking to do as you start finalizing the relationships, thinking about where some things are going to end up in your overall design. Think about where the structural elements are going to go relative to that, just how you're going to place them all relative to each other. So we'll be thinking about that a little bit together in that. I think it's really hard to sort of think about the envelope without thinking about the structure, because we're kind of figuring out individually. Okay, in terms of the integrated design project and where you should be this week, please go ahead and sign up for some check-in times. We posted a couple this afternoon, there's some tomorrow afternoon, some on Thursday. We'll see how it goes in terms of if our Friday works out too, but just go and just try and sign up for a time, see if something's convenient for you. If not, we'll try to schedule some other ones. We are, at this point, going to be thinking about the whole notion of, you really want to have, your building kind of preliminary design looking fairly complete this week. So you really want to have a fairly kind of firmed up notion of really the overall building layout, how the spaces are organized and arranged, where they're located, what the circulation paths are, kind of where those big utility spaces are. And then for the building envelope, we're really going to start thinking about all those different surfaces, the north side, the east side, the west side, and different spaces that have views, really what kind of surfaces we're going to think about and why we're choosing those surfaces. Are they solid? Are they glazed? Are they ultra-insulated? Just all the kind of nuances, really what you can be thinking about and why you're kind of making some of those choices for the building envelope. And everyone's project will be a little bit different in terms of how you want to think about that. So you're moving more from sort of big boxes and forms that are organized well into something that has an articulated surface. And you'll keep on moving as we go from here a little bit, but at a high level, it's really good to get these sorts of things at least preliminarily nailed down so that you then have a steady basis to work from, because we're going to start adding structure and mechanical to your building, and it's going to be good if these things are relatively steady so you can position things relative to them. If later on you continue to move things a little bit, that's okay. If you're going to move things radically, for example, if the restrooms are where they need to be when we start doing our plumbing, you'll sort of do it once. Whereas if you need to move it radically, then you'd have to end up redoing some of the mechanical systems. So the idea is to get at least in the right neighborhood, so that later on when we start putting in more detail, you don't have to do a whole lot of rework. Even as we keep on going, I think there's always some things that we learn as we start putting the mechanical systems in that force us to start thinking or rethinking some of the things about the way we lay out our building. And I think we all, at the end of this class, get to this point where we think, if I knew it all way back when and had to do it over again, what I would start to do differently. And those are always good things to kind of think about, but I'll encourage you not feeling like you have to go back and fix everything constantly, because as new things are discovered, you don't always have the time to go back and sort of fix everything. It's kind of hard because you're working on a moving target, so you're changing the wheels as the bus is moving, and it's really a little bit tough sometimes to get it all done at the same time. Okay, so be thinking about nailing some of that stuff down and checking in with us, and we'll give you some guidance about how the overall envelope is looking. Okay, there's also a new exercise kind of floating around out there in Canvas. This one's really based on the building envelope, and really it's a kind of pretty standard just sort of building shape where at a high level you're supposed to go through and sort of make some of the surfaces glazed, make some of the surfaces solid, and just have some rationale for why you're doing that. Okay, so just to give you a little bit of practice with trying with some different surfaces and how you might approach it, kind of on a very simple building. Again, just sort of practice with that independent of your building, because your building's always a much harder thing to kind of really think about in detail about how you're going to organize it. Whereas for my little sample buildings, like it's my simple little L-shaped building, it's pretty easy just to go ahead and play with things and feel very creative. So that's floating around out there. Again, these are always that. Do not spend much time on these. Just got to get there and sort of get some fluidity with exercising the Revit tools, exercising the modeling tools, and get it turned in. This is really, there's not much to it. So they're just there to give you an opportunity to practice a little bit, on something that's an easier form. Okay, in terms of the building envelope overall, the big high-level things that we sort of got into in thinking about the envelope are, there's all these different aspects. There's walls, there's windows, there's shading features, all sorts of things where for each of them there's different design considerations. As we're thinking about windows, there are things that we think about in terms of how we arrange them, basically how they sort of appear and what sort of views they frame, whether they're going to be sort of curtain walls or sort of individual windows that are in the wall. There's also all sorts of different performance things to think about. So there's windows that are very, very high performance, that make sense to apply in some places, but maybe not everywhere, because having a very high performance window actually has some cost associated with it, so you may want to save it for the places it's going to do the most good. So with walls, same sort of things. As we think about walls and you're making your decisions there, there's all sorts of material considerations. What do they look like? What is their texture? All these aesthetic considerations, but there's also a performance side. And I think that's sort of true of all the different things we think about. It's this funny trade-off and balance between sort of the aesthetic considerations and the performance considerations, because if we all had just incredibly high performance boxes, that probably wouldn't be a very satisfying aesthetic experience. Okay, but you also want to sort of introduce performance as one of the things you care about, because it's not strictly aesthetics either. Everything we do is sort of a balance. Okay. We're going to look today specifically at the notion of lighting and shading features and how they work. And you're going to find that there's a number of ways we can start to provide shading. We can do, on the inside, we often have rolling shades or shutters or something that's on the inside is blocking out sun when we don't want it, and move that away when we do want the day lighting. On the exterior, there's all these things we can do that typically are features of windows or of the roof. So roof eaves and roof shading is one of the strongest things that's very easy to do, or sort of a canopy or an awning over a window. But also we can build in things like light shelves and light fins to go through and provide some shading right on the window. And we're going to play around with that a little bit today. We'll also look at roof surfaces. In terms of roof surfaces, for the most part, we tend to think of them as being just shielding us from the heat and the cool, and kind of providing very insulated surfaces. But we also have this whole notion of green roofs. So we can think about how roofs can actually be terraces or usable surfaces too. And how you can actually take advantage of some of that. So let us go ahead and just play around a little bit in terms of exploring some of these different things and how they might affect how we analyze things. Okay, but the big thing is ultimately, it's all a question of balancing. There's what we're trying to use and capture versus what we're trying to protect ourselves from. And for everything, there's always this sort of trade-off. For everything that is a positive, I'll give you a negative, or everything that's a negative, I'll give you the positive side of it. There's always sort of a balance between forces. And just depending upon what our local climate is, you may want to go through and approach it differently. Or, often developing a layered strategy so that these different things can work together. But let's go ahead and talk about kind of the building envelope, and to do that, we'll kind of illustrate some things and also kind of play with these analysis tools. So you looked a little about the daylighting analysis tool. We'll play around with that some more. but we'll look at the solar and the energy tools too. So I'm going to go to Revit, and I'll start by just creating a very simple little structure, and we'll go from there. So I'm hanging out over here in Revit, and I'm going to just create a new architectural template. I have a lot of sample models that are available out there that we can go through and take a look at, but I'm going to build up some stuff just organically first. These sample models illustrate a lot of different daylighting conditions, but let's see if we can sort of get a sense of really what's going on ourselves. So we're hanging around in Revit. If I start thinking about the simplest building form, I'll just put some walls in. Architecturally, I'm going to start thinking about them having specific properties as opposed to being generic, because as I think about the properties, that says a lot about what the thermal properties are going to be. So I have all these brick walls, I have these insulated foam system walls, I have some CMU walls. I'll use this EIFS system. That's kind of a very common system that we're using a lot for commercial buildings these days. I'll say that the wall height just goes up to level 2 for now. Place these walls. I'll make my standard L-shaped building, which we all know about. I was going to say know and love, but no one loves this building, actually. Okay, so we got the walls in there. Right now, I just have sort of a very boring envelope right now. There's not much to it. It's really just kind of this expanded foam system typically has like a stucco kind of texture on the outside. So not too awfully interesting, but it does have some thermal properties, so we should take a look at that. If I go through and look at it and I edit the type, you'll see that it currently has a really good R value of 66. And that is because, just property-wise, it has a lot of foam in it. It has a lot of rigid foam insulation. So if you want to sort of look at that or start thinking about any specific wall construction, under the structure, as you're assigning the different materials, this is where the R values get computed. So if, for example, in this case, I think most of it's actually happening for this EIFS. It's actually the foam on the outside. We can look at each of the different materials. If it's 3 inches of foam, it's giving us a 66 R value. If I say that instead that's going to be, like 2 inches of foam instead, it's down to 59. It's actually sort of interesting. As I look at this, I think our air layer is actually giving us the biggest, 0.4. That's giving us a 72. So I'll put it back to 0.3. But each of these different materials has some sort of thermal properties associated with it. You can actually check them out. This is some sort of cellular polyurethane boards. It has some isotropic behavior, so it has a density and a specific heat and a thermal conductivity. But all those things add up to say that as we typically go through and increase things every inch, if it's a sort of a linear behavior, the R value will continue to increase in a linear way. Okay, so if I wanted to have a higher R value, what I would typically do is to basically go through and add some more thickness, 3.5 or 4 inches or whatever it is. And for all of the different walls that you're going to be working with, we'll kind of think about really what is the layering that you want. We'll create another one. This is a very highly insulated wall, so this is actually probably higher insulated than most walls that get constructed. Let's look at a different kind of construction. For example, if anyone's done any residential construction, okay, kind of typical residential construction, let's see if we can construct a wall that sort of feels similar to that. If, for example, let's see if I find anything in here. I don't have anything that looks like a nice little wood frame wall, but I'll go through and make one. What I can do is really start with any of these as a beginning point. Maybe I'll work with that one as my starting point. If I want to create a new wall construction, for example, let's say we wanted to go through and create a wall, let's say it's 2x6 studs, something like that, nice little wood frame wall. It'll have some plywood on it and some gypsum board on the inside, pretty standard. Maybe we'll put some rigid foam insulation, like an inch or 2 on the outside, and then like wood siding on the outside. It's a very common kind of wall, or we put stucco on the outside, just some sort of construction like that. it will look like this. I'm going to say, let's just change duplicate. I'll say exterior, say 2x6 plus rigid insulation plus siding. Okay. So that's just a name, but let's go ahead and build it out now and sort of see what actual properties we have in there. So these are all the properties that are kind of hanging around in here right now. One that I'll start with is just messing around with the structure. That is the actual core of the wall. Currently it's a metal stud layer. If I want to put wood in there, I'll change that to 5.5 inches for 2x6s, which is always sort of confusing. And let's see if I have some nice wood framing in here. Actually, I think even in here, there's probably, it's called stud. Let's see if that, it's a metal stud layer. I don't see a nice wood stud layer. Try lumber. Softwood lumber. Okay, there's all sorts of different materials in here, but I sort of want to, I'll leave it as softwood lumber for right now. There's sort of an interesting thing about the way Revit does it in terms of really what we want to think of that as being. In a funny way, that's actually not even truly the way I want to think about it from a thermal standpoint. I could think of it as actually being the insulation that's between the studs, because that's really where we're getting most of the thermal value, is that insulation. So if I change it to bad insulation, which is just another way to think about it, that might give me a truer value. Maybe I'll switch that over to that insulation. I think I do have that. Wood joist rafter layer, bat insulation, or fiberglass bats. Well, let's go for a fiberglass bat for right now. You'll see it has some sort of properties to it. So if I go through and put a 5.5 inch bat, that actually is looking like a pretty heavy duty. Okay, let me go through and take out some of these other ones. I probably still do have a plywood layer, although that may be, 1/2 inch or 5/8 of an inch, something like that. Infiltration, I'll take that layer out. Well, the bat's just a barrier. I'll leave that in there. This is where I'll change it around a little bit. For my thermal air layer, as opposed to just having 2 inches of air, let me go through and put a little rigid insulation in here. Now that's an awful thick wall, so let's maybe just only 1 inch. Super. Okay. And now we can go through and think about the exterior finish. The exterior finish, this expanded insulating foam system, that's actually got an awful lot of like insulation right there. If I wanted to make it more like wood siding or something like that, I can change that too. So the idea is you're just going to create as many different kind of wall types as are necessary. So like siding, clapboard siding, that sounds fine. Okay, that's actually much thinner. Maybe, 1/2 inch or 3/4 of an inch. Okay, you'll see that actually made a huge difference. This wall was like an R70 some odd prior, and now it's an R47, which is probably a lot more realistic. So that 1 inch of rigid insulation is actually raising it. It's actually not too awfully bad. If I needed to have a thicker, kind of more insulative wall, I could raise that to maybe more rigid insulation. Or I could take that out if I didn't need that so much. That's a R51 wall. As we go through and construct walls here in like Northern California, who knows, like, what's the R value that we typically assume for a wall sort of in the Bay Area? The Bay Area is considered a fairly mild climate. So you have a sense of like how big the R values are, the thermal resistance values? Yeah, I do. Like, how about for a typical house? Like, what do you think the R value is, the walls in the home where you live here in Palo Alto? You know, you can even think in the home where you live, not in Palo Alto. 35 would actually be a very insulated wall. Just give you a sense. Who lives in an old Eichler home or one of the older homes in Palo Alto? Anyone live there? Does everyone live in Escondido Village? Okay, very good. In the high rise or the low rise? So you're in an older building. Is it an older building or a relatively new building? It's old? Okay, so what do you think the insulation value in that is? 25 would be quite good. My guess is it's probably R13. R13 insulation. The way it works is typically fiberglass mat insulation, if it's 3.5 inches thick, is R13. If it's 5.5 inches thick, it's R19. Okay, and you can think of those numbers and the relationship really being very directly related to how much heat flows through. So an R19 wall allows for 13 over 19, that ratio of the energy to pass through. So R19 really is quite a bit better. So having an R51 wall is actually quite good. It's quite a bit better than like the walls are in most of our homes. I live in a home that was built around 20 years ago. It has 2x6 walls. It's probably like R19 or something like that, maybe R20, something like that. But it's probably in that range. So when we start thinking about these walls, they're really much better. The walls we build today, because why should we have things like the rigid insulation and stuff like that? Let me just try this. If I took out the rigid insulation completely, let's just try that out. It's going to complain at me a little bit. That's 1 foot, R92. Let me just take it down to delete it. That's an R43 wall. In my sense, this fiberglass bat number is actually too high, but I'm not going to worry about that. We'll need to fix that sort of at a higher layer. Okay, I'll say thermal air layer. I'll put the rigid insulation back in there. Super, and I'll put that in like an inch. So great. I got a nice wall type. You can have the same wall type on all sides, or you can vary it around a little bit. But let me just kind of span around here. And I'll make them all the same type. Super. So we have some walls. They're kind of hanging around looking pretty good right now. Let's go ahead and put some windows in these walls. Okay, so if you just kind of think of a standard window, a window that plugs into the wall and opens, it might open top to bottom or left to right. We have some fixed windows here in the default project. We can plug those in. We can get a double hung window if we want to, or a casement. Let me put a couple fixed windows in. Now, fixed windows are kind of okay. Fixed windows don't move though. You can sort of look out them. They're good for getting lighting in, but they're not very good from a ventilating standpoint. So that's probably not the best window. Let's see if we can find one that actually ventilate. So if I say insert, and I go to the windows, let's take a look. A casement window is not a bad one. A casement window, just in terms of all our funny terminology, casement windows have a hinge on the side and they swing out. Okay? As opposed to an awning window. An awning window has a hinge at the top and it swings up. Okay, so one of those. Double hung windows are the ones where you have the two different panes and one slides past the other in a vertical direction. And the other kind is called a slider. A slider is two panes side by side. And they do that. So they're all just different variations on that. If you were contrasting them, for example, a slider window is kind of a good one. Let's go to put that in there. It's a very common one. You'll find that in a lot of houses and buildings. Let's kind of drop that one in there. So that's a slider, horizontal slider I'll sometimes call that. You can sort of see the two different surfaces kind of moving past each other. I'll contrast that with, let me put in a casement window instead. So let's get a window and put a casement one in there. It's a single casement. They also have double casements. They open from the middle. Let's do the double casement. Okay, so let's talk about these different windows. Actually, those three are all kind of comparable. They're all about the same size. They're not quite the same size, but close enough for what we're up to right now. 36 by 48. I'll see if I can make that 36 by 48. Well, if I don't have the size, those of you who've kind of been hanging with me through the Revit classes Know that it's easy to go through and create a new one by duplicating the type. And I'll put the 36 in there as the width. Excellent. Okay, now they're comparable. Okay, I got these 3 different windows here. In terms of just thinking about them and how much, let's think about different perspectives. In terms of how much, for example, view they're allowing, are they similar or dissimilar? Look at that. I'd give them a similar. There's a little blockage in the middle, but not too often. If it was a big window, they're pretty good on view. How about on daylighting? Is daylighting going to be pretty similar on those 3 windows? Yeah, they're all going to be pretty much the same. It's, there's a little blockage because of that little part in the middle. But yeah, I'm not going to worry about that frame too often much. How about in terms of ventilation? Okay, so this one's fixed, the glass doesn't move. This one panel slides past the other. This one, they both swing open. Okay, so if you were thinking about trying to capture some cool natural breezes or something like that and use natural ventilation, this one's out of the question. That's not doing you any good at all. That lets the light in and the heat in, but no ventilation. This one sort of opens halfway. Okay, this opens the full way. Okay, so you say, well, gee, how come we don't put these in all the time? That would seem like a much better thing to do. Just kind of have them all swing open and capture all that ventilation and stuff like that. You think of any reason why you might not want to use that window? Yeah.
When it rains, you get rain on the sides of the windows and it can rot.
Exactly.
Open.
When they're open, okay, a couple things. It's a little more expensive as a window goes because it has hinges on both sides, so that's a little more expensive. But there's this whole issue of when they're open, like the inside's sort of exposed. So it could get rain in there, and that can kind of get exposed that way. The other thing that happens, if you ever kind of have these on the outside of a house, there's a walkway going by, and someone has the windows open, those windows stick out into the walkway. Okay, so, it's a little bit of a blockage thing. Yes, Ruby?
Is there any safety issues when it comes to high-rise buildings? Like kind of the relation just allows you to use certain kind of windows?
It's interesting in that, these types of windows which open very freely are probably not a good call in a very high-rise building, because if they opened all the way and for whatever reason, whether it was a small kid came near it, or a pet, or even you get near it and you trip, that would be very dangerous. So often in high-rise buildings, we use a variation of windows like this. It'll often be, in fact, let me do the single casement. The windows in other parts of the world are actually far more sophisticated than we typically use here. Let's load in a single casement window. Right here. Oh, come on, you. Hang on. It's going to complain at me just because of how I'm loading it. Let's load it in this way. Single casement. It's kind of related to what you're asking about. Okay, it's a casement window. Looks an awful lot like a fixed window. These types of windows, especially in different parts of the world, are set up in a way that you can open them just a few inches, which is good for ventilation, but they don't swing all the way out. Especially in like a high-rise building, having it swung all the way out may not be a very good thing, because when the wind's whipping past, that could create a lot of load on the window, or something like that. So, but what's very cool about these windows in some parts of the world that we're doing is they have them so that they can swing out, or when you close it, you can swing it down. So it's like it's got a hinge on the top and a hinge on the bottom. And you can sort of, just depending upon what you need, go through and kind of introduce ventilation in a couple of different directions. Usually what will happen then is if they're going to swing all the way out, there's kind of a special lock. But yeah, they're all pretty similar in terms of that. Okay. If you were thinking about this in a very practical sense, I do a lot of residences, so I'm always thinking about fire egress and having to be able to get people out of bedrooms through a window. Okay. In that case, the fixed is no good. Okay. The casement window or the double casement are good. You get to sort of count the whole area of the window as being a possible evacuation route. The slider window is limited, that you can only count half of it, because even when you open it, only half of it's available. Okay, so different things about that. So lots of different choices in terms of windows. Now sometimes we put windows way down low like this. Another strategy though is like all these windows are, those I'd say are good view windows. They provide a view outside. If I'm looking towards the lake or something like that, they're very, very good. If I'm thinking about, rather than trying to get a view, I just want to get daylighting into a space, I could think about putting windows in a slightly different way. I could go through and, let me just do it with the fixed windows. Take windows which have more this shape. Oops, wrong way. I'll switch that over. What I'm thinking about is a long window that is not very tall. So, I'll just switch that around. I'll edit this type. I'm thinking about more a window which is not 24 by 48, but 48 inches by 24. So it'll be 4 feet wide and 2 feet tall. And I'll go ahead and put them up here at the top of the wall. And you'll find windows like that. If you see windows up like that are at the top of the wall, kind of like these are polycarbonate panels, but the same idea is that basically you're trying to get light in, but you're not trying to get a view in there. Yeah. Often very useful in classrooms and public spaces. If, for example, right behind me at this very moment, as interesting as I am, if there was a big glass window over here and people were walking by and waving and doing whatever they're doing back in there, your eye cannot help but watch that, because we are animals and somehow programmed to look for things that are moving because that might be dangerous. So you'll pay attention to what's back in there. So often in classrooms or auditoriums or things like that, if there are windows, they'll sort of be out of the view line because you don't really want to be distracted by what's going on behind you. So yeah, lots of things, ways of thinking about windows. Now let's talk about our windows from a energy performance standpoint. Okay, so I got a bunch of windows hanging around here. You might remember that wall had an R value of, what was it, like 50 or something like that. Okay, 47. Okay, so let's think about on this little building we're building here, I got heat. I got heat that's kind of either trying to get in or get out, or cool that's trying to get out. Like, how do the windows and the walls compare to each other? So, yeah, this value of the wall right now is around 47 or something like that. What do you think the R value of the window is? What's kind of a typical R value for a window? That's a pretty good guess. It actually is sort of similar to that. It's very, very low. Let's check it out. All these windows actually have some parameters built in that we can sort of change. It really depends on the type of glazing. Is it single glazing? Is it double glazing? Is it low-E coated? There's all these different sort of things you can do. But this window right now, which is 1/8 inch single glazing, is a R value of 1.5. Okay, so what does that mean? If this wall over here has an R value of, say, 45, and this is 1.5, that means the wall is 30 times as resistive as the windows. Or, real roughly, you can think about, inch for inch, 30 times as much energy passing through that window as passing through the wall. Okay, which is why we care about so much about windows in terms of what's going on with their thermal performance, because if you're looking at, a building and trying to kind of really control the climate and the natural forces, like the qualities of the windows really tends to be very much important. The qualities of the wall, we're pretty good about insulating those so those don't become a big issue. So much of our attention gets focused on the windows. So you can play around, even in Revit, you can play around with different types of glazing, different U values, different E values for low emissivity glass. So for example, I could do a double glazed window. that goes anywhere from a 2.8 that's about the same. That's going to get into sort of this is the solar heat gain. Let me try this and that. Okay. In the low emissivity glass, the thermal resistance is about the same, but the solar heat gain coefficient is a little bit lower. If I change it to a higher rating, the solar heat gain is going to be higher. So there's a lot of different coefficients. And you can ask whether these are all good or bad things. It kind of depends on what you're trying to do. Thermal resistance, that's just if you're trying to cool the building or keep the building cool, yeah, that's heat's going to leak in, or you're trying to warm the building, heat's going to leak out for that. Solar heat gain's got an interesting one, because that really says for all the solar radiation which is hitting the window, how much of that is going to actually be captured as heat and get in that way. So I also think about the right direction for this. If it has a high coefficient, I think then more of the heat's getting in. If it's a low coefficient, more of the heat's being blocked. Okay? And whether that's good or bad really depends on your condition. If you are in a condition where you're trying to actually capture the heat from the sun, you might want to have a higher coefficient. If you're trying to shade yourself because you're in a very sunny spot and your problem is that you need to air condition all the time, you probably want a low coefficient. Okay, so all of these things ultimately get modeled, so we can change these values. You can even try, oh, there's very exotic glazing in here too. Let's say triple glazing. Triple glazings give me an R value of 3.9. Now, you may say, hey, that's not all that great, but actually 3.9 compared to 1.5 is doing pretty good. It's at least twice as good, a little bit more than twice as good. You can even go for, oh, if you look really hard in here, you can probably even find quad glazing. There's triple. Maybe I can't find quad. An air partition. See how much difference it actually makes to be triple glazed, quarter inch. No, the thickness of the glass doesn't help that much. Okay, so you can go ahead and find different values you want. And ultimately this is all going to factor into kind of the thermal performance. So when you go through and you run thermal performance calculations, let's go ahead and we'll put a little more on this. Before we can do any sort of thermal performance, I should probably put a floor and a roof on this, just so we can kind of capture the heat. So let's do that. I'll put a floor in here. Now, floors themselves actually have properties, so if you're really going to care about the thermal performance, don't just go living with this generic floor. The generic floor has an R value of 0, so you'll have heat leaking down through the floor. So think about what you wanted to put in there, whether we'll put in some nice kind of concrete slab. Doesn't have a nice concrete slab, I better make one. I'll duplicate that and call it a concrete slab. Okay, oh, maybe a 10-inch slab. Put a little cast in place concrete here. There we go. Maybe 10 inches here. Let's talk about this. Okay, I got this 10-inch slab. This 10-inch slab is kind of doing pretty good. One thing that my 10-inch slab has going for me is check out this thermal mass number. Thermal mass is a pretty good thing if we're trying to think about storing heat and using it later. So a concrete slab like we have here in our building, the sun shines down, all that radiation gets absorbed into it. Think of it as a big battery that just soaks up all that energy and then radiates it out at night again. Something like that in cooler times. So we tend to like thermal mass in places where we're going to try and use heat over and over again. It's often passive solar design we do that. 18 points is actually really good at thermal mass. You'll find that the walls have a very small thermal mass. They're not very good at all. So this concrete is pretty good. Okay. The R value though, 1.3, that's not very good. All this heat's going to come leaking out through this floor or something like that. Let's go ahead and think about, oh, well, that's not very good. What if it was 12 inches? 22 1.6. Well, that's not very good. What if it was 2 feet? 3? Okay, that's not very good either. So you can say, well, that's not very good in the scheme of things. Let's talk about whether that matters or not. Okay. In general, if your concrete is on top of the ground, and the ground has a relatively constant temperature of, who are my good earth science people? What's the temperature of the ground? Like, are they, when you're in the ground, it's like in the 60s. There's a certain distance when you go below the surface, it stays constant at a certain temperature. In general, the temperature of the ground is pretty good for what we want. But it's still, if the temperature of the ground is 60 and you're heating the building to 70, there's a heat loss to there. It's not as bad a heat loss as the heat loss going to the 30-degree outdoor air temperature. Okay, but it's still something to worry about. So it used to be we would rarely go through and put insulation in slabs, but now we do these days because we're realizing that's a significant source of heat loss too. On the ground, it's not so bad. If you've got a concrete slab above, for example, a garage that's open and exposed, then that's a big source because all that heat goes down kind of through the concrete. So if I wanted to add a little insulation, I could do that. And usually what we'll do is, underneath it here, I'll put a little thermal layer in here and maybe put some rigid insulation in there. Okay, maybe I'll put like 2 inches of rigid insulation in there. So that brought it up to 9.6. Again, that's not huge, but it's 4 times as great as it used to be. If I did 3 inches, it'd be up to R13. So we often put a little insulation in the slab too. New, we didn't used to do that. But we're getting such high performance buildings. Here's really what the rub is. We have gotten so good at creating energy efficient buildings that now things that didn't used to matter. Because as you seal up everything and make it incredibly good, it'll always find the weakest link. So if the weakest link is the floor, that becomes your problem. So that's why we care about that now. We didn't used to so much. Okay, I got that. Oh, I better sketch something. I have a lovely floor, but nothing to sketch. Okay, let's just put some boundary lines in there. Gonna grab these walls. Actually, little tricks, Revit tricks. I'm gonna hover over one wall. If I tab, it'll get all the walls. So, quite a quickie Revit trick for doing that. Okay, I also need to go through and put some sort of, roof on this thing. We're gonna do our energy performance. So, for my roof, let us think about this. Okay, I'm going to put it at level 2. That's fine. As we're tracing our roof, again, roofs have properties, so that generic 12-inch roof is doing you no favors because it has 0 thermal resistance to it. So if we're going to actually sort of get an accurate energy model and worry about the walls and the windows, we have to go ahead and worry about that thing too. As a starting point, you might take a look at the wood rafter, 8 inches. All of these have a certain amount of thermal property to them. I'm just going to use that wood rafter for right now. Let's kind of check out its properties. Looks like that has an R value of, what, about 57. That's looking pretty good. Okay, super. Let's go through, here's an interesting question, overhang. So typically, we have some sort of overhang on our roof. We could put no overhang, but then when the rain comes, it would just kind of like wash right down the wall. So we typically put a little bit of overhang just to sort of protect the walls. It's more about, weatherproofing that. But it also has a good benefit in terms of solar radiation, and if we have too much heat, kind of blocking out some of that. We can do an awful lot with our overhang. But as a starting point, just put a very modest overhang of around 1 foot on my building, and come zipping through there, coming around. Okay, this is currently sloping on all sides. I'm going to make it flat just because that'll be a little bit easier to understand. I can do that by either sort of setting the slope to 0, or I can choose all these different lines and just turn off this defined slope. Either one of those will have the same effect. Okay, we are ready for some thermal analysis. Okay, so let's just kind of take a look at this. Oh, just to make this a little more interesting, we'll put some more windows in this thing. Put some big windows in here. We'll put some on the south side, we'll put some on the west side. Actually, as we're doing this, I have not been at all careful about giving this thing a location, so let's give it a location and an orientation. So, oh, where do we want to put our building today? What's a good spot? How about, I'm gonna go, I always do cold weather climate. I'm gonna put it in Dubai, or how about in Delhi? Delhi is actually sort of a good spot. Is it D-H-I, or is it definitely in New Delhi? D-E? Thank you. That's like, do you ever have words that you know you misspell? Like I can't spell the Philippines either. I always put the it on the wrong side in terms of where the P's are. It's got New Delhi right there. Okay. I like New Delhi in that it has a very different climate than what most people expect. Although you may know better. Okay, so we have, okay, a climate, we're doing good here. Just so you know, right now, this project is oriented towards the south. This is the south side. We can change and rotate that a little bit as necessary. This will work for now. Okay, so great, we got this. We can go through and do all sorts of analysis. Actually, one other thing to do. It's kind of funny. I'm not sure if it's absolutely necessary these days. It used to be necessary, so I'm going to do it just to be on the safe side. Is I'm going to put a room in here, because a lot of things depend on rooms. Like the daylighting analysis depends on there being a room and a floor. But let's go ahead and put one of those in just to be on the safe side. I think energy may work without it now, because I think it sort of assumes that there is one. I'll go level 1. As I'm putting my rooms in, watch out for this. Make sure your room is tall enough to be sure to hit the ceiling. So even though it's only about 10 feet tall, I'm going to put it at 15, just because I want to be sure to hit the ceiling. Okay, almost there. Other thing to do on rooms, to be on the safe side, is by default rooms don't compute the volume, so I'm going to turn that on, because for our energy purposes we need that. Okay, so I got a good looking little building over here, and, well, it's not so good looking, but it'll take care of what we need. We'll look at energy analysis, so 2 different types of analysis. Actually, we can do all 3, really. Let's look at each of them. We'll start the energy first. I'll say under the energy tools, we can say energy settings. We can say here we are, we're an office building. That would be important, kind of how many hours a day it operates and how many people are in there. If we use rooms as our category, it's going to use this setting. If we're actually using spaces, which is sort of a finer way that we'll get into using, or we can control a little bit more what the function of each individual rooms is separately, we'll change to that. But let's say office, okay, use building elements. This is all we can find in there. If we go through and, include thermal properties. That's a big one. If you don't, it'll sort of apply some defaults, okay, which are under the conceptual constructions. If we've actually gone through here and put in real R values, we'll actually want to use those. So put that in there. There's always something to get myself in trouble with. Super. I'll just leave most of these set to default since we're not changing them yet in meaningful ways. So, okay, we are ready. Now, you may not realize it, but there's actually been an energy model created. And if you want to take a look at it, you can say it's right next to energy analysis. There's the create the energy model. See that? Okay. That's what the energy model actually looks like. What it's done is, for all those different areas, it's gone through and created a volume. It's created different surfaces on the volume. Each of those different surfaces have thermal properties. This is a lot of what we used to do manually, but that's really what the energy model is. If you ever sort of wonder whether or not your building is being represented accurately, you can always sort of look at the energy model and You can try to figure out, if some of the surfaces are warped, or sometimes when you do this, you can tell that the room volumes don't actually extend up to the roof, things like that. So you have like holes in your energy model. But this looks good. Let's go ahead and I'll just say, let's run some simulation on this. Okay, and we'll use that. I'll even update the energy model. I didn't change anything, but I just want to be certain. Okay, let this go off and run. And I think this is where you were last time. Okay, I'm just going to call this is my session 7. Spring 2016. Just let that go off and run. Now, since it's running off in the cloud, it's going to take a few minutes to do its thing, but it'll actually go pretty quickly. While it's doing its thing, we'll start some other analyses too. We'll do the daylighting and the sun too, so we'll look at all these different things. Based on my very primitive envelope so far, but there's enough there to kind of get us going. So, if we want to take a look at this envelope, let me go just back to the default 3D view. Okay, and we wanted to, for example, kind of look at the whole issue of the sun hitting the windows. We looked at the sun kind of in a conceptual sort of form, and whether it's hitting the windows. If you want to actually sort of see what's happening with the solar analysis kind of on your real building model, you can choose the solar analysis tool. You can sort of say, do you want to just hit the roof surfaces, or do you want to hit all the different surfaces? I'll say disable that. If I only want to get the roof surfaces, well, I'm just getting all the mass. I'll say all my surfaces. Then let me go through and select some. Hang on. Solar energy. Let's go to that one. That's fine. I'm looking for something, and it's not showing me what I expect to see. I expect to see something that's going to let me choose the different walls. Hang on here a second. I'll try this just with the roof surfaces. Try that first. Okay, what is it doing? I gotta see where I am right now. That's not doing anything. Okay, so it's up to something. I just haven't figured out what yet. Now you're gonna work. Now you're not working. I'm looking for an error message of some type which tells me that it's busy. Oh, well, the energy analysis is complete. We can go over and look in there in a second. But in the meantime, this is not doing what I want. What are you doing to me? I can't say close it. It looks like it's busy there.
We were doing this on last Thursday.
Same thing?
Yeah, we were having a lot of trouble.
Let us figure out what's going on. Because usually what happens is a little like in the options bar up in here, there's something that basically says you're selecting surfaces, and then you can like choose, then finish selecting the surfaces. So let's see. I'm just going to go looking because there's something weird going on. Okay, we can get the window. We won't close the window. That's kind of interesting. So what is going on with this little analysis tool? I don't want to crash it. What I'm going to do is, I can still save it. That's okay there. I don't know. Let me go look at the energy analysis. We'll look at that, and at the break, we'll take a look and start see if we can figure out what's going on with why that tool is doing that for us, because that's not very good at all. Okay, for energy analysis, if you want to kind of check your results, what you can do is In the energy analysis tools, there's this part that says results and compare. We can come on over here. Oh, it's kind of behind this window right now. See if I can find my session 7. It's right down there. So let's take a look at what this thing is telling us. Here we are in beautiful New Delhi. What is happening here? Oh, the maximum outdoor temperature is a balmy 114 degrees Fahrenheit. The minimum temperature is 36 degrees Fahrenheit. That's a hot spot. Okay, our floor area is around 2480, exterior wall area. It figures as an office, about 9 people could be in here. Okay, we have some different energy use information in terms of the energy use intensity. The good news is, although it is so incredibly extreme out here, we have a very well insulated building. We built a very tight building so far. So it's even for the extreme weather condition, the energy use is not all that unusual. What we want. You can see that, now check this out. This thing, we have the energy use. We're going to find out most of it's being used by electricity, and I bet most of it's for cooling. Okay, although the PV potential there is actually quite high, so if you put some high efficiency panels, we could actually be generating energy on this building as opposed to using energy. So that's kind of attractive. So we can think about the economics of whether that makes sense. In terms of the energy use, let's take a look at it here. You'll see, most of it's electricity, and if you go down and sort of see where it is coming, the fuel use almost all is happening for domestic hot water, and most of the energy, it's kind of sort of evenly split between lighting and aircon. So lighting's are on this side, down there actually aircon's over here. Actually, lighting's smaller in this one. You'll see that our heating load is actually very modest. In fact, we're only going to do a little bit of heating, if at all, during January. Okay, and for that, of all the different surfaces from a heating standpoint, as you go looking at what are the things that make sort of the biggest difference? The way to read this is all the things below 0 are heat losses, all the things above 0 are heat gains. Okay, so if I just looked at where I was losing, say down below there, what is the biggest source of loss right now? Yeah, okay. So it looks like window conductive is the biggest loss. So if anything, I might look at the U value of the windows to make that a little higher if I was concerned about that number. It's probably not the biggest number I'm concerned about. The second one is, can you check? It's actually infiltration. So just leakage around the windows. Okay, so we can look at putting in a higher performance window that's really tight, something like that, or just really the infiltration going. For the most part, the roof and walls, I'm not even going to worry about. Let's look at the cooling side. The cooling side, okay, you got all those different things. Everything up here, above here, is really contributing to the cooling load. So I got a lot of miscellaneous equipment. I got some light fixtures. There's not much we can do about that with the envelope. Okay. Oh, the biggest thing I'm looking at here is, what's the orange? It's like window solar versus window conductive. So what that's telling me is if I'm thinking about those windows, it's not so much a U value issue. It's not how much heat I'm conducting through. It's really how much solar energy I'm getting through that's creating that load. So I might think about the E value of the windows to try and cut down on the solar heat I'm getting through the windows. Or I might think about putting some window shades on there, some sort of either a roof overhang or something that's blocking the solar. Okay, but what's going to happen is everyone's building is going to be different. I can take this very same building and I'm going to put it in Moscow. And we'd have a very different problem. We'd say, great, bring on the sun. I need more insulation in the walls. There's like different considerations for every building. But what these charts are all about is it gives you a lot of information to start understanding for your envelope, where you want to kind of focus your energy or focus your attention. Okay. Let's go back and order Revit and see what's going on there. that's really kind of vexing about what's happening here. So how about this? Let's go ahead and take our break now. I will see if I can sort of figure out what's going on with where does my mouse go? Why can't I close that window and get that solved? But I want to take a look at the daylighting and then start mucking around with this like building a little bit so we can like explore some different scenarios about how we can kind of improve and change it. So let's go ahead and take our break and come on back in 5 if you can.